Have you ever actually stopped to think about what physically happens when millions of people are simultaneously streaming a 4K movie, running complex AI algorithms, or just, backing up their photos? The physical servers processing that colossal amount of data generate a staggering, almost incomprehensible amount of heat. Like if we just left it unchecked, the very infrastructure of our digital world would literally melt down in a matter of minutes. Keeping these data centers alive requires something most of us never see. It's a massive, hyper-precise, and entirely invisible nervous system of sensors.
Welcome to this explainer. I'm absolutely thrilled you're here with us today. We're going to completely unpack the raw data and the source material behind this massive cooling infrastructure. Think of it as a spatial journey. We'll be tracing the vital signs of the cloud, starting from the massive multi-ton outdoor cooling towers and going all the way down to the delicate, microscopic chemistry of the indoor water lines. So here's our tour route for today. First, we'll look at the macro level with the cooling towers. Then, we dive into the heart of it all, the distribution units. Third, we'll zoom into the micro level to check out water quality. Fourth, we'll hit the front lines at the server racks themselves. And finally, we'll wrap up with exactly why all this precision cooling actually matters.
All right, let's jump right into Section 1, the macro, looking at cooling towers.
We're starting our journey outside, at the absolute macro level, looking specifically at the data for unit LCS, SCLT, 01C1001. Now this is where the heaviest lifting happens, literally rejecting massive heat loads generated by the data center out into the atmosphere. And here, we really need to demystify two absolutely critical acronyms, PUE and WUE. That's power usage effectiveness and water usage effectiveness, which our source data measures in liters per kilowatt hour. Think of these as the high-level vital signs for the entire facility. The sensors on these cooling towers, they aren't just checking local temperatures. They're actively calculating these facility-wide efficiency metrics to make sure the building isn't just wasting massive amounts of electricity or municipal water.
And this brilliantly illustrates exactly how this tower balances the micro and the macro. On one hand, you've got mechanical sensors checking their own physical status, right? The system is monitoring the basin heater, it's checking the water basin level height down to the literal millimeter, and tracking the RPMs of fans 1 through 4. But simultaneously, and this is the cool part, these sensors are managing massive facility-level loads. They're tracking the total heat load in kilowatts, the instant power total, and the facility water flow rate in liters per minute. It's really this perfect marriage of mechanical self-awareness and facility-wide responsibility.
Moving right along to Section 2, the heart, which means the distribution units.
So, stepping off the roof and going inside the facility itself, we find the coolant distribution units, or CDUs for short. If the cooling towers are the lungs of this operation, these CDUs are absolutely the beating heart. They pump the critical lifeblood, which is chilled water, throughout the intricate veins of the server room. And the most crucial point to take away here is this staggering number, 29. According to the source data, there are 29 distinct individual sensors constantly monitoring just a single distribution unit, specifically unit LCS SCDU 1K3LR001. This single machine is incredibly instrumented, tracking everything from primary supply pressures in kilopascals to return temperatures in Celsius. It ensures the pulse of the coolant never falters.
To really put that level of precision into perspective, just think about your laptop or your home computer for a second. It probably has, one or maybe two internal fans, right? Well, just one of these industrial CDU units, Unit 050AR030, requires 10 independent fan percentage sensors just to breathe. We're talking fan 1 through fan 10, all being continuously monitored and modulated. This is brilliant because it means if even one fan starts to underperform, the other 9 can dynamically compensate on the fly to keep that coolant flowing without even a single degree of temperature fluctuation.
Next up, Section 3, the micro, focusing on water quality.
Now we're zooming in dramatically from that heavy machinery all the way down to the microscopic chemistry of the water itself. And it's a fascinating contrast, really, because in a data center, water isn't just water. It's a highly engineered thermal transfer fluid. The CDU's nervous system is actually split between two totally different worlds here. On one side, it's measuring what I like to call brute force metrics, so tracking raw kilowatts of instant power consumption and primary heat removed. But right alongside that, on that exact same unit, it's tracking delicate chemistry metrics. It's looking at the water's pH level, its electrical conductivity in microsiemens per centimeter, and its turbidity, which is basically just how cloudy or clear the water is. Why do all this? Well, because even slightly acidic or highly conductive water could cause catastrophic corrosion or electrical shorts right inside the cooling loops. To maintain that absolute chemical perfection, the system relies on this really intense level of water pressure monitoring. On this specific CDU, we're seeing sensors for the filter inlet pressure and then hypergranular sensors for filter 1, 2, 3, 4, and 5 outlet pressures. By measuring the pressure drop across 5 separate filters in kilopascals, the system knows exactly when a single filter is starting to catch particulate matter. This intense monitoring ensures the cooling liquid stays purer than a municipal swimming pool, which completely prevents those microscopic blockages that could choke the server racks.
That brings us to Section 4, the front lines, the server racks themselves.
We've finally arrived at the end of our physical descent, right at the front lines of the data center, the individual server racks. Looking specifically at the sensor array for unit SRK42RDCC, this is exactly where the cold air and chilled water finally meet the screaming hot microchips. And what this proves is that cooling isn't just some general blanket effect thrown at a room. Heat behaves dynamically, right? It rises, cold air sinks. The data center's nervous system knows this, so it actually feels the environment spatially. The rack has dedicated sensors for the top, the middle, and the bottom. It measures server outlet temperature, outlet air temperature, and air pressure specifically at those up, middle, and bottom positions. So if a specific server at the very top of the rack is running some massive AI workload and getting super hot, the system knows exactly where that heat is localized.
And how does it react to those precise spatial temperatures? Well, the rack uses a suite of dedicated, highly specialized sensors to dynamically adjust on the fly. It constantly calculates the dew point temperature in Celsius to make sure condensation absolutely doesn't form on the electronics, because that would be a disaster. It monitors the exact water valve opening percentage and the water flow rate in centimeters per second to inject more cooling right where it's needed. Plus, it tracks the RPMs of 5 dedicated EC fans directly on the rack to push that cooled air exactly over the hottest components. It's just a brilliant, highly localized response to heat.
Finally, Section 5, why precision cooling matters.
So zooming back out from those individual server racks to the entire massive facility we just walked through, why does this all matter? Why go through the immense expense and crazy engineering effort to track hundreds upon hundreds of hyper-specific data points every single second? Well, because everything you do online, literally every email you send, every video you watch, every single financial transaction processed, it all generates physical heat in the real world. These countless invisible sensors form a resilient nervous system keeping the digital world alive. Without this hyper-vigilant, intricately connected infrastructure monitoring everything from giant fan RPMs down to microscopic water clarity, the cloud we rely on every day simply couldn't exist. It would just burn itself out.
So I'll leave you with a provocative thought to ponder. If just one essential water valve sensor fails out of hundreds, how long until the cloud literally melts down? We so often think of the internet as this intangible, magical thing floating up in the sky, but it's deeply physical, heavily reliant on water pressure and temperature. The incredible resilience of our connected world balances on the continuous, flawless operation of thousands of tiny, invisible sensors. Thank you so much for joining me on this explainer to decode the nervous system of the cloud. I really hope this gave you a brand new appreciation for what happens behind the scenes every time you click refresh.